As an application of coupled systems of ODEs, we're going to look at a mixing problem where now we've got two tanks. So we're going to have X1, this is going to be the mass of the solute in the first tank, and V1 is going to be the volume of the fluid, the solution, in the first tank. And so X2 will be the mass in the second tank, and V2 will be the volume in the second tank. And we'll have the rate of the incoming stuff, that'll be coming in terms of volumes per time, and concentration of the incoming, so that'll be in terms of mass per volume of the solution. And then the same with the outgoing, the rate out will be given in volume per time, and the concentration of the outgoing will be mass per volume. And just like before, the concentration of the outcoming will actually be the concentration that's in that tank that it's coming out of. So that'll be X1 over V1. And now we've got these two new quantities of Q1, the rate at which solution is pumped from tank 1 into tank 2. So that's also going to be a rate in volume per time. And then we're going to be pumping it back from tank 2 back into tank 1. So it'll mix and then get pumped and then mix and then get pumped, and some of it will be coming out and stuff will be coming in, and it'll be a right jolly complicated mess. Now, the good news about all this is that the equation for setting it up is exactly the same as it was before. So that is the time rate of change of the mass of the solute is going to be rate in times concentration of the incoming minus rate out times concentration of the outgoing. Sort of ran up against the edge there. Let me pull this back a little bit and fix that. Got a little crazy there. All right. And so when we multiply these two quantities together, this will give us something in terms of units of mass per time, which is the mass rate of change that we're looking for, as opposed to this part right here, which is our flow rate, and is in terms of volume per time. Those are our givens, rate in, rate out. Okay, so let's see. So we just need to set up this same equation for each of the two tanks. So for tank 1, let's see, we're going to have X1 prime, time rate of change in X1. So that's going to be, and then we look at all of the things coming into tank 1. So we're going to have stuff coming in here, but then we're also going to have stuff coming in here. So from the first one, we have R in, C in, and then from the second one, we're going to have a rate in of Q2 times, and then the concentration of the incoming here is going to be the concentration in tank 2, which is X2 over V2. So that's incoming minus outgoing. And so the outgoing for this situation is what's coming out through this one right here. So that's going to be Q1 times, and then the concentration of what's going out through that tube, which is the concentration in tank 1. So we have this equation. Now we set up what's going on in tank 2, and here we have X2 prime, which is, let's see, so the incoming is what's coming in right here, so that's going to be Q1 times the incoming concentration, and then minus, I'll put these in parentheses so that it sort of jumps out what's what. And we'll subtract Q2 X2 over V2 from what's going out this way, but there's also what's going out this way. So that means we need to take into account R out times X2 over V2. Okay, so rewriting this system a little bit, we have, in collecting terms, we have X1 prime equals minus Q1 over V1 X1 plus Q2 over V2 X2 plus R in C in. And we have X2 prime, which is going to be Q1 over V1 X1. And then we're going to be subtracting R out plus Q2 over V2 times X2. Okay, so there's our system set up. I'm going to space this a little bit so that you can see exactly what the coefficient matrix looks like. Yeah, put this guy over here. And so you can see that we set this up as a matrix equation with x prime given by minus q1 over v1, q2 over v2, q1 over v1 minus q2 plus r out over v2 multiplied against x, and our forcing function r in c in 0. So if we were also dumping some stuff into the second tank, maybe here we'll put a little hopper funnel on here, and we're pouring stuff into here. Okay, that's not the best, but whatever. Okay, then whatever information this would be right here, let's call it R2. R into R2, good enough. Then that would be contributing to some forcing function right here, stuff coming into the second tank. But we won't be doing that for this particular problem. And so also, I guess it's worth pointing out that all of this, all of the information intrinsic to the system, so like what's going on, in this part right here, this is all expressed by what's happening in the system. The forcing, what's coming in from the external world, is the non-homogeneous part right here, just like we've seen before in other examples. And so if the V1T and V2T are constant, so in other words, for the first tank we need R in minus Q1 plus Q2 to equal 0. And for the second, we need to have R out minus Q1 plus Q2 equal 0. Then we have a constant coefficient system. And so what I'm saying is that if these orange rates balance in that the signed sum of them is equal to 0, and if these let me pick a different color. How about here, pink? These ones balance, then the volume of the fluid in this tank will remain constant, and the volume of the fluid in this tank will remain constant. And that means that all of these numbers right here are going to be constants as well. And we'll be able to use the techniques that we've been working with. So if you want to memorize this system right here, okay, be my guest, you can do that. Or if you just want to remember this basic idea here and set up the equations, you're welcome to do that too.